everybody. Today we're going to be taking a look at some applications of exponential functions. So we're going to take a look at three sort of different examples to sort of lead you into what you're going to be working on in class. So here's our first example. Ms. Adams' Toyota Camry was purchased in 2007 for $21,000. It depreciates in value by 25% per year. How much is it worth today? When will the car be worth $100? So the first thing we have to do is sort of model what's going on in this scenario. Now, the car that we have here is going down in value. That's why it's depreciating, because the value of the car is going down over time. So we would call this exponential decay. So what I want to do is I want to come up with a decimal value for how that is decaying. So I'm going to come up with this model. Let's call it f of x. Now I'm going to start with 21,000. That's my principal amount, or that's what I started with. That's what the car cost when I first bought it. And since it's going down 25% per year, this is going to model what remains. So if 25% is leaving this price, that means that 75% is remaining. Now that's happening per year. So I'm going to take this decimal and raise it to the x power, where x equals the time in years. Which makes sense because after the first year, I would take 21,000 and multiply by 0.75. After 2 years, I would take 21,000 and multiply by 0.75 twice. After 3 years, I would take 21,000 and multiply by 0.75 3 times, and so on and so forth. So we can maybe write also that f of x equals the car's value, okay, or how much the car is going to be worth. So the first question says, how much is it worth today? Well, what year is it? It is the year 2013, which means that in 2013, it has been 6 years since the car was purchased. So we're going to do f of 6. So 21,000 times 0.75 to the 6th power. And if I do that on my calculator, that tells me that the car is worth about, right, because we're probably going to be rounding some decimal, $3,737.55. So the second question is, when will the car be worth $100? So in this case, I'm giving you what the car's value is, and I'm looking for how much time has passed. So in this case, you're given f of x and you're looking for x. You're looking for the time. Now, later in the chapter, we're going to learn how to solve this by hand, but right now we're going to solve using the calculator. I think the best way to do this is to probably graph 21,000 times 0.75 to the x and y equals 100. So you might want to take out your calculator now, maybe pause the video and type these two functions into your calculator. And you're going to get that point of intersection right there. And we're going to get that that point of intersection is 18.587, 100. Okay, so that means after 18.587 years, the car is going to be worth $100. So in 18.5 years, which is what year? 2025? Okay, so in 2025, the car will be worth $100. So it's important that you answer the question in complete sentences, right? If I give you a word problem and I ask you all these questions, it's important that you answer the question that I'm asking. Don't just sort of box your answer or circle the number. It's important that you write your answer as a sentence. Okay, let's take a look at another one. Okay, example 2. A radioactive substance has a half-life of 4 days. The substance begins as a 32 milligram sample. How much is left after 8 days? How much is left after 19 days? So let's take a look at these words here. This is half-life, a half-life of 4 days. Now what that means is that every 4 days, the substance gets cut in half. The amount of the substance gets cut in half. So let me just make a quick table here. I'm going to call it f of x even though I don't have a function yet because I'm going to get one. But at 0 days, I have 32 milligrams. Now, it takes 4 days for that to get cut in half. So after 4 days, I'll have 16 milligrams. After 8, I will have 8 milligrams. In 12 days, I will have 4 milligrams. 16 days, I will have 2 milligrams. And it's going to obviously continue on forever in that way. So how can we come up with a model for this? Well, I'm going to start with how much I have. So I'm starting with 32. Now, again, this is going to be exponential decay because my substance is decreasing in amount. Now, by how much is it decreasing? Well, every 4 days, it gets cut in half. Okay? So my decay factor in this case is 0.5 or 1/2. Now, we have to be careful because there's a difference between time in total and when this substance actually gets cut in half. So I have 2 parts to my exponent here because I have the time in days, but that's not necessarily the same as how often the substance gets cut in half. So then I also have to take into account the length of the half-life. So we'll call x the time in days, and we'll just use the letter n for the length of the half-life. So I'm going to multiply this 32 here by a half every multiple of 4. So I need to take the total time that I'm looking at and divide it by the length of the half-life. Does that make sense? Because after 16 total days, my substance only gets cut in half 4 times. So of course, this 4 here is going to change based on the information given to you in the problem. So let's see how many is left after 8 days. Now we have that in the table. After 8 days, there's 8 milligrams. But if I do out f of 8, I get 32 times 1/2 to the 8 over 4, which means I get 32 times 1/2 squared, which is 32 times 1/4, which is 8. So after 8 days, there's 8 milligrams. Of the substance. Now, we have to take a look at what happens with 19 days. You should already be noticing that 4 does not go into 19 evenly. Okay, so this is going to be an interesting answer. So we have 19 days is what we're asking about. So we're going to do f of 19 equals 32 times 1/2 to the 19 over 4. Okay, now you have out your calculator, so I would sort of do out this math in your calculator. Now, you know, if I look at my table, 19 is going to be after 16 but before 20. So you know that your answer to after 19 days should fall in between 1 and 2 milligrams. Okay, and if you do it out, it actually does because it comes out to 1.189 milligrams. Okay? Okay, let's take a look at one more example. Okay, here's our last example. So there's a lot going on here, so let's just sort of talk about all the different variables that are happening in this case. Mrs. Trader puts $10,000 into a savings account that earns interest at an annual rate of 2.75%. So let's start with the fact that we have the money that's going to be in the account. So we're going to call A the amount of money in the account. Okay, so of course we have to start with something. So in this case, P, which we call our principal amount, is $10,000. So that's what you originally put into the bank. We have R, which is our interest rate. Okay, so what the bank's going to give us. We have T, which is the time in years, right? So obviously I'm going to get a certain amount of money, or I'll get more money, I guess, if I leave my money in the account for a longer period of time. And then we have N, and N is the number of times the interest is compounded, and I'll tell you what that means in a second. Number of times the interest is compounded per year. So what that basically means is that if you ever take a look at a bank statement of a savings account, usually you are continuously getting money a certain number of times per year. So the bank's not just going to take your money and at the end of every year give you 2.75% interest. What they'll do is they'll sort of split that percentage into a bunch of different payments. So maybe they'll pay you twice per year. Maybe they'll pay you 4 times per year. Maybe they'll pay you every month. Maybe you get a couple of extra dollars every month. They're splitting that interest rate into 12 payments. Maybe they give you a couple of cents every day and they're splitting their interest rate into 365 payments per year. So most banks do this and they sort of decide how often they want to give you interest on your account. So the model that we're going to make is going to be a growth model, right, because your interest is getting added on to what you start with. So we have our principal amount times 1 plus something, okay? So what are we adding to it? Well, we're adding our interest rate divided by how many times per year that happens. Then I'm going to raise that to, again, the number of times per year that happens times the number of years. Okay? So in my case here, A equals 10,000 times 1 plus, we're going to turn that 2.75 into a decimal, 0.0275, over N raised to the NT. So what changes will be how many times it's compounded and how many years it's in the account. So let's say that they compound your interest monthly. That means that N is 12. That means you're getting some amount of money every month. So that would look like this. A equals 10,000 times 1 plus 0.0275 over 12, all to the 12 times T. Okay? And T can be whatever, 5 years, 10 years, 2 years, whatever's going on there. What if they compound your interest daily? Okay, that would look like this. A equals 10,000 times 1 plus 0.0275 over 365 days per year, raised to the 365t. Okay, now I'm not going to do out these numbers for you. You can do that yourself on your calculator, which I think that you should do before coming into class, and think about which one of these is better. If you're putting your money into a bank account, would you rather have your interest rate compounded monthly, or would you rather have it compounded daily? Which of these two gives you more money? And why do you think that is? Okay, so be prepared to talk about that in class. Which one of these two gives you more money, and what do you think the reasoning is behind that? Okay, everyone, good luck with your word problems.